Myself, Adinath Kadam. I am MTech machine design student from VJTI Mumbai. The project title of mine is Analysis of Hot Box for Structural Integrity. A company named Hempen Metals and More. They manufacture hot isostatic pressing furnace for the manufacturing of net-shaped parts. Now, how this layout looks like? This is the HIB furnace. This is the skirt support, and they are joined together by a welding, which is TIG steam welding, and they are facing. They are facing problem of weld cracks in this weld zone. So the project objective is to analyze this weld region and to minimize these weld cracks and actually to eliminate all these weld cracks. For this particular paper, I have restricted my study to get a relation between radius of this hemispherical end, then half length of this pressure vessel and the skirt support height. I am going to get a relation between these three parameters. Next. Now, what this hot isostatic pressing furnace? It is a furnace which is used for manufacturing of net-shaped parts, whose weight is ranging in between 10 kg to 15 tons. And this furnace utilizes the basic principles of powder metallurgy, then basic fundamentals from casting and forging technology. Next. Now, HIB, this furnace mainly is working on these two principles. The first one is elimination of closed porosities in castings of sintered parts. Now, here these powder particles are placed in a container and very high pressure is applied on these particles so that all the porosities are eliminated. And then high temperature is applied over there. Due to high temperature, which is around the sintering temperature of these particles, the particles which are in intimate contact with each other, local welding occurs at these points, as it is indicated over here, and these particles aggregate together to form the final product shape. Now, the process which is followed here, first they form a container which is like a mold, which is of the final shape part. Then through the intake, they put the metal powder into this container. Then they evacuate this chamber and close that intake. And then they place this container in the HIB furnace and apply high pressure and high temperature. Once the process is done, they remove this container to get the final product. Now, this is the HIB furnace. They will put this container over here and they will apply high pressure and high temperature by using some inert gas like argon, so that no chemical reaction will be taking place within the pressure vessel. Now, as I told, the operating conditions for this pressure vessel are very high pressure and very high temperature. The temperatures, for example, can be in the range of, say, for a particular operation, it can be around 600 degrees Celsius, and the atmospheric temperature will be around 20 degrees Celsius. Now, as I told you, if we consider this as a pressure vessel, then the temperature over here, let's take it as 600 degrees Celsius, and outside temperature let's take at 20 degrees Celsius. Then across this thickness and welding is done over here. Across the welding zone, the temperature difference that is occurring is around 580 degrees Celsius. So very high temperature difference occurs across that particular zone. Due to this high temperature difference, very high thermal stresses are getting induced. And because of these stresses, thermal cracks are observed in this welding zone. So I am working on this particular zone. Okay. So what is this welding phase? Now, as I told, this pressure vessel is not a storage vessel. It is actually a process vessel. So if the welding fails, then the whole entire system and installation equipment will fail. Then moreover, due to if here the welding fails, then due to some sudden impact or something, as it is subjected to very high temperature and pressure, it may result in life risk. And moreover, as the weight of the net-shaped parts which are placed in it, they are ranging to few tons. Then if the process fails, then that much of huge weight of loss we can't tolerate. Next. So what I am introducing here is the concept of weld box or hot box. The hot box is nothing but an insulation kind of a ring provided like over here. Now, if we consider this as the insulation, then heat flowing across this section will be restricted in this zone. due to which temperature in that zone will increase. And as the temperature increases, the temperature difference across this weld zone will reduce, and hence the thermal stresses and all these consequences will be avoided. The FEA analysis will be consisting of two stages. First one is the thermal analysis, where I am going to impose the thermal conditions. Then I am going to convert these thermal conditions into structural stress by using commands in ANSYS. And for this particular analysis, I have taken into consideration only thermal stresses. For doing that, I haven't taken its weight of the total system into consideration. The elements used are for thermal analysis I am using plane 77, and for structural analysis I am using plane 82. The basic advantage of these two elements is that they are isoparametric in nature, due to which any curved portion which are present in the geometry, they can be perfectly fitted. As I told you, this is a skirt type of support, and the pressure vessel is also axisymmetric. So instead of going for 3D analysis, I can convert this problem into a 2D analysis by using simple axisymmetric case. Next. Now, the area of concern is only this weld region. So there is no need for having any analysis of the upper portion. So I can give symmetry command over here, and I can consider only half portion of the pressure vessel. So I will consider only half length of this pressure vessel. Next. For meshing, I have taken into consideration AE size command in ANSYS, which allows me to just tell the software to take element size as 20 by 20 square, and it will then divide the flow geometry in those many elements. Next. For this particular, what I am doing, I am taking this as the radius, then half length of skirt support, half length of pressure vessel, and this is the skirt support height. I am taking ratio of this radius to skirt support height as constant, and for a particular radius, I am varying this height from 50 mm and 100 mm in steps of 100 till I get an optimum value. What that optimum value is, I will let you know after. And the basic assumption which I have taken into consideration that hemispherical end, then this shape and this skirt support, they are glued together in ANSYS. Readings taken are maximum stress value in the whole geometry, stress value at this particular point, which is the area of concern, and maximum deformation in the whole geometry. Now for a typical analysis, where inner radius is 1000 mm, length is 500 mm, and height of skirt support is 1200 mm, I am getting these values of maximum stress and maximum deformation. For that particular zone, I am getting maximum stress over here, and this is the weld region of my interest. Now, for a typical analysis, say for 2000 mm radius and constant skirt support height, I have varied half length of vessel from 50 mm to 100 mm, 200 mm, and for each step, I have calculated sigma max and sigma at the weld zone, and for each step, I have taken percentage increase in sigma max at weld zone, and I have done that till at a particular value. I see that the percentage increase is only less than 1%. So I can restrict the optimum value to 1300 mm. Sorry. So for a particular radius 2000 mm, when I vary the half length, I am getting the stress value, and this variation in stress value is getting diminished as we go along the increasing the half length. Same for 5000, and for 7000 we are getting almost a straight curve. Next, now I have plotted. I have varied this radius, and for each radius I have plotted the optimum half length, and beyond the particular value, say 7000 mm, I am getting a very constant optimum value of pressure vessel. So from this I can conclude that for a given R by H ratio, I can restrict the value of half length so that I will get only a percentage increase of 1% in stress value, and while designing the system for given R, H and L, I will just check if the given value of half length is beyond that optimum length. If it is so, then I can take directly the stress calculations. All those are ready for me. I will take that for optimum length, and from this graph I can conclude that beyond 7000 mm the main contributor to the stress analysis is the radius of the hemispherical vessel and not the half length of the pressure vessel. Sir, by using there is one command TTS where thermal to structural analysis, thermal elements are getting converted into structural elements. In solver, I will do this.
Just one minute, can you just explain physically why that will be like halfway to the line?
Yes.
Just
I
open
have not
the
taken all those
last.
Second last.
Just give us a physical insight as to what is happening there.
So here we are getting first grid and then diffuse. So your question is quite.
No, it is quite obvious from the graph. What I am asking is, can you give a physical explanation
Yes.
of that variation? If you know that